So for this video, I am going to try to teach you about limiting reactants for Chapter 9, Section 30. Before we jump straight into the chemistry side of things, I figured it'd be easier to look at maybe a more familiar example. So if you were having like a picnic or something, or a cookout, and you wanted to make hot dogs, so here you have 5 hot dogs and 4 hot dog buns. Well, when you have this, you of course can't make the most of the hot dogs. You're limited by the buns because with the hot dogs, of course, we have 1, 2, 3, 4, 5. We know that we have to combine the hot dog and a bun in a 1-to-1 ratio. And here we only have 4 buns. So the most that we can make is 4 hot dogs. Okay. Most we can make is 4 hot dogs, and it leaves us with a leftover hot dog. Here, in this case, what's stopping us from making that last hot dog in a bun? What's stopping you is the fact that you don't have any more buns. So when something stops you in chemistry, we're going to call that a limiting reactant. Okay? This is what's going to eventually stop us from making more hot dogs in the bun. Now, in terms of a hot dog, we would call this an excess reactant, or something is in excess. And so over here, we actually have 1 hot dog left over, so it's in excess. Whereas the buns are going to be limiting us from making more hot dogs in a bun. Now we can apply that same hot dog in a bun concept to an actual chemical equation. So here we have hydrogen combines with oxygen to form water. So in this case, down here below, we can talk about these. So this represents an H2 molecule, and this represents an O2 molecule. So when we have these, we look to our chemical equation. For every 2 H2s and 1 O2, we can produce 2 waters. So, and that's our ratio. Remember, that's going to be our mole ratio. That's what we have to have going forward. We can't have half of an O2 molecule. It's for every 2 H2s and 1 O2, we produce 2 waters. So if we think about this, okay, for every 2 H2s, so here's 1, 2, and 1 water, we can produce, or excuse me, and 1 oxygen, we can produce 2 waters. So if you follow the purple, that's what's been consumed so far. Now let me switch to a different color. I can switch to something like, we can just do green. Now again, for every 2 H2s and 1 oxygen, we can produce 2 waters. Now let's try and go back and do it a third time. We have 1 O2, but we're all out of hydrogens. So we have an oxygen left, but we're all out of hydrogens. So therefore, this extra oxygen is just that. It's excess. So oxygen is what's going to be in excess. What is stopping us from producing more waters? What's stopping us from producing more waters is the fact that we don't have any more hydrogens left. So in this case, H2 is going to be what we call the limiting reactant. Okay, and of course our excess reactant is going to be our oxygen gas. So here I've pulled a sample problem from the book on page 298, and hopefully we can take what we just learned qualitatively and apply it to a problem. So silicon dioxide is quite unreactive, but reacts readily with hydrogen fluoride according to the following equation below. If 6 moles of HF is added to 4.5 moles of SiO2, which is the limiting reactant? So here we have, again, I'm just going to write things underneath, 4.5 moles of this and 6 moles of this. Now, in order to solve these problems, the first thing that we need to do is pick a product. And that's going to be the product that we're hypothetically going to make given this certain amount of moles. You can pick silicon tetrafluoride, or you can pick water. You can get the answer whether you choose either one. So I'm just going to select silicon tetrafluoride, as my target product, and I want to see how much of silicon tetrafluoride can 4.5 moles of silicon dioxide make. And then I want to say, okay, how much can 6 moles of hydrogen fluoride make of silicon tetrafluoride? And the way we want to do this is we want to pick one. So I'm going to pick 4.5 moles of silicon dioxide first, okay? It doesn't matter which reactant you pick first. I'm going to pretend that I have an abundance of HF. So HF isn't a problem, all right? I have a ton of it there. I want to know, given that HF is going to be constant, how much silicon tetrafluoride I can make from 4.5 moles of silicon dioxide. And the way we're going to figure this out is use our mole relationships. So for just looking at my chemical equation, for every 1 mole of silicon dioxide, we produce 1 mole of silicon tetrafluoride. And again, these are our mole relationships, right? That's what our chemical equation tells us. So this math is, of course, super easy. These cancel out and everything's just 1. So 4.5 moles of silicon tetrafluoride. So what this says is, given 4.5 moles of silicon dioxide, we can make 4.5 moles of silicon tetrafluoride, assuming we have an abundance of hydrogen fluoride. Now, the next thing we want to do is do the same thing, but for hydrogen fluoride. So we're going to kind of flip it. So we have 6 moles of hydrogen fluoride. Assuming that silicon dioxide isn't a problem, we have an abundance of it, we want to know what's the maximum this 6 moles of hydrogen fluoride can make. So for every 4 moles of hydrogen fluoride, there is 1 mole of silicon tetrafluoride. And again, I'm just using our mole relationship here, 4:1. If you do this math, moles of HF cancels out. It gives you 1.5 moles of silicon tetrafluoride. Now, again, it's very important that you also did this one for silicon tetrafluoride. You don't all of a sudden want to switch and do it to water here. That's comparing apples to oranges, okay? You want to stick with and do this stuff for the same product. So just looking at these mole relationships, this 1.5 and 4.5, we can see that 6 moles produce less of the silicon tetrafluoride than the 4.5 moles of silicon dioxide. So therefore, okay, this 1.5 moles is less. And this came from 6 moles of hydrogen fluoride. So we could never get up to 4.5 moles because we would run out at 1.5. So therefore, 6 moles of HF, or you can just simply say HF, is the limiting reactant. It is literally what's making us, or what's preventing us from making an abundance of Si4. So in this case, again, HF would be our limiting reactant. And you can also do the same thing for water. If you didn't want to choose silicon tetrafluoride and do this for water, that's fine. You just have to make sure you do them both for water. The next example I'm working comes from page 299. It says some rocket engines uses a mixture of hydrazine and hydrogen peroxide as the propellant for the rocket. The reaction is given below. Part A, which is the limiting reactant in the reaction when 0.5 moles of hydrazine is mixed with 0.5 moles of hydrogen peroxide. So first things first, we need to pick a product. It doesn't matter this one. How about this time I'll pick hydrogen, or excuse me, should pick water. Okay, I'll pick water as the product. So for this one, I have 0.75 moles of hydrazine and 0.5 moles of hydrogen peroxide. I'm going to choose one. I'll choose with hydrazine, and I want to see, given an abundance of hydrogen peroxide, how much water this can make. So 0.75 moles into H4. We always start with what we're given. And now I'm going to move into my mole relationship. For every 1 mole of hydrazine, it can produce 4 moles of water. Throw this in the calculator. And this can produce 3 moles of H2O. I'm going to do the same thing for hydrogen peroxide. We have 0.500 moles of hydrogen peroxide. For every 2 moles of hydrogen peroxide, there are 4 moles of water. Throw this in the calculator, and we end up with 1 mole of H2O. So because this is the smaller quantity of the two, that's going to mean hydrogen peroxide is the limiting reactant. Now for part B, it says how much of the excess reactant in moles remains unchanged. I kind of went ahead and switched to a blank slide to help us, or to give us a little bit more room. But, just to recap from the last one, our hydrogen peroxide is going to be our limiting reactant, which means our hydrazine is going to be our excess reactant, and we're still working with the same moles from part A. Now, what part B is asking us is how much of the excess reactant in moles remains unchanged. We know that all of this, because it's our limiting reactant, is going to be consumed in the reaction. We're not going to have a problem. All of that is going to theoretically go away. However, we know that hydrazine is going to be left over because it's going to be the excess. Part B is asking you how much is left over. Okay, so we need to calculate that. And it's not as easy as just saying, oh, well, let me subtract 0.500 moles from this, and oh, okay, well, in this case, 0.25 moles must be left over because that's when you subtract it and that's how it works. That's not how it works. We have to remember our mole relationship, okay? For every 1 mole of hydrazine, 2 moles of hydrogen peroxide is consumed. So therefore, we can't do this, okay? We can't just simply subtract out the moles. I know it seems logical to do that, but because of this relationship, you can't. So we just need to start and use our train track method to figure out exactly how much of this hydrazine is going to be consumed. So if we're starting out with 0.005 moles of hydrogen peroxide, let me make this moles. Okay, we use our molar relationship. For every 2 moles of hydrogen peroxide, we can consume 1 mole of hydrazine. Okay, so moles of hydrogen peroxide cancel out. 0.5 divided by 2 gives us 0.25 moles of into H4 is consumed. Consumed. Okay. It wants us to know how much is left over, how much remains unchanged. So we're going to take our original starting amount of hydrazine, 0.750 moles. Okay, that's what we started with. We know, based off of the stoichiometry, 0.25 moles are going to be consumed in the reaction, and that's going to leave us with 0.500 moles of hydrazine left over, or in excess, or as the problem wants you to, as it puts it, unchanged. So 0.5 moles remains unchanged. For the last problem here, this is going to get a little bit harder than the ones before. We have iron oxide, which can be made in the lab according to the equation below. When given 36 grams of water and we mix it with 67 grams of iron, which reactant is the limiting reactant? Now, in previous problems, it's given us moles to start out with. Here we have grams. This is just going to be one of those extra little annoying steps. Remember that grams and grams don't react with each other. Only moles react with each other. So in order to compare these relationships, we need to convert this grams into moles. So we can do that. I'll just do it right up here. 36 grams of water using the molar mass of water. 18.02 grams for every 1 mole of water. This is going to give us 2 moles of water. And I will write that right here. 2 moles. For iron, we'll do the exact same thing. We have 67 grams of iron. There is 55.845 grams in every 1 mole of iron. This is going to give us 1.2 moles. Oops, why isn't it writing? 1.2 moles of iron. And I will write that up here. 1.2 moles of iron. Now, our next step, this is where it's going to be similar to the problems that we just did. So, you can pick either product. It doesn't matter. However, I'm going to have a little bit of foresight in this one, and I'm going to pick iron oxide as our target product just because I saw in part B, it already asked us something about iron oxide. Again, in order to find the limiting reactant, you can pick the hydrogen gas or iron oxide. It doesn't matter. I'm just strategically choosing iron oxide in this case. All right. So I need to pick one of the reactants. I'll pick the iron first. So we have 1.2 moles of iron using our molar relationships. For every 3 moles of iron, there is 1 mole of iron oxide. And that gives us 0.4 moles of iron oxide produced. The same thing for water. We have 2 moles of water. For every 4 moles of water, we produce 1 mole of iron oxide. This gives us 0.5 moles. In order of which one's the limiting reactant, you're always going to go for the one that produces less. So in this case, 1.2 moles of iron can only produce 0.4 moles of iron oxide. So our limiting reactant is going to be the iron. So iron is the limiting reactant, which I'm just going to abbreviate with LR. Now for B, it says what mass in grams of black iron oxide is produced. So in this case, we know that iron is going to be our limiting reactant. We've already established that, okay? This is limiting reactant. I can only produce as much as 1.2 moles of iron will produce. Well, you know, if you want to start from the beginning, we can say, okay, well, how much does that produce? We already did that math right here. All right, but if you're not following me on that, we can just do it again, that's fine. So 1.2 moles, I want to know how much iron oxide can be produced, and specifically it's asking in grams. So we have 1.2 moles of iron. For every 3 moles of iron, we can produce 1 mole of iron oxide. Okay, that gives me 0.4 moles of iron oxide. And again, this is going to be our same as what's up here. Okay, that's the exact same thing. It wants to know in grams. Well, you can go from grams to moles by using the molar mass. In this case, the molar mass of iron oxide is 231.5 grams for every 1 mole. Moles cancels out, and that is going to give us 92.6 grams of iron oxide. So for every 1.2 moles of iron, we can produce 92.6 grams of iron oxide. All right, just real quick, carrying over from the previous slide, what we already determined was that Fe is the limiting reactant. We can produce 92.6 grams of iron oxide. Also, a few other things. We said that this was 1.2 moles, and this was 2 moles. And this is, again, the limiting reactant. If this is the limiting reactant, that means that water is the excess reactant. So looking at part C, what mass in grams of the excess reactant remains when the reaction is completed? So again, we know that based off the limiting reactant, all of the 1.2 moles of iron is going to be consumed. We need to figure out how much water that actually consumes. So for this, we're going to have to do our mole-to-mole relationship between iron and water. So for that, we have 1.2 moles of iron, which we know is going to get all consumed because that's a limiting reactant. And then for our relationships, for every 3 moles of iron, 4 moles of water is consumed. This means, if we of course do the math in the calculator, this means that we are going to get 1.6 moles of water will be consumed. So if 1.6 moles is consumed, we have 2 moles to start with, right? So 2 moles of water to start with. 1.6 moles of water is consumed in the reaction. And so this leaves us with 0.4 moles excess or leftover, or however you want to put it. So it says, what mass in grams of excess reactant remains? Well, again, we figured out moles. It wants to know in grams how much is left. So we just convert grams to moles like we normally do. So this is 0.4 moles of water. For every 1 mole of water, there is 18.02 grams. That is going to give us a value of 7.2 grams of water. Okay? And so that's going to be our answer for part C. Hopefully this video helped you. If you have any more questions or have any more problems you want me to work, just send them over and I will be more than happy to do so.